This is 3.6, deviation from the ideal gas law, also known as real gases. So our outcome is I can explain non-ideal behavior of gases based on inner particle forces and the volume occupied by gas particles. So the properties of gases are explained macroscopically using the relationships of pressure, volume, temperature, moles, gas constant, and we can even compare them molecularly by looking at their motion. So properties are macroscopic, motion is molecular at the molecule range. So, ideal gas law gives us approximate behavior of gases, but it fails to do so under a wide range of temperatures and pressures. So, that's because those assumptions of the KMT are only accurate under certain temperatures. So, if we look at our ideal gas law equation, PV equals nRT, gas particles do experience attractions and repulsions, which is going to impact their pressure. And gas particles also take up space, which is going to impact their volume. So, deviations from the ideal gas law result from interparticle attractions among gas molecules, especially at conditions that resemble condensation. Deviations can also arise from particle volumes, particularly at high pressures. So, what conditions are going to give us our ideal behavior? So, ideal behavior means the intermolecular forces are minimized. So, that's going to be high temperature, low pressure, large volume. So, we have our ideal gas law equation. We also have a real gas law equation. It's also known as the van der Waals equation. So, in this equation, there are a couple of corrective factors, A and B. So factor A alters the pressure in the ideal gas equation to account for those intermolecular forces. The size of A indicates the strength of intermolecular forces. It's got some funky units. Notice that we have pressure in ATM, so we have to make sure that unit cancels appropriately. B accounts for the volume occupied by the actual gas molecules. So B corresponds to the total volume occupied by gas molecules per mole. It very closely corresponds to the volume that we would get per mole of liquid state. So A and B values generally increase with the size and complexity with the molecule, and A is usually much smaller in magnitude, or B is usually much smaller than A. So in our first question here, I want you to calculate the pressure on this gas with these conditions using the ideal gas law and then using the van der Waals equation. So I identified my variables here and I solved for my pressure using just the ideal gas law. Then I went and did it again, this time using the real gas law and using my corrective factors here. And we see that my answer is different than what I got with the ideal gas law. Now we're going to do the exact same calculation, but this time with a volume of 10 liters. So when I solve that with both ways, I get the same answer. And that's because at 10 liters, those intermolecular attractions and the volume of the individual particles have less of an impact because the volume is so much larger. So we see that for some conditions, the ideal gas law is good enough. We get the same answer as we would get with the van der Waals equation. But under other conditions, it's not the same. And that difference could be a very large difference depending on the properties of the gas. So comparing our results from question 2 and 3, how does increasing the volume impact those interactions? So at the smaller volume, those particles are more likely to interact, and this is going to increase the intermolecular forces, making the gas behave non-ideally. At a larger volume, we see that we have more idealized behavior. So at that smaller volume, we see there is a difference in the calculated pressure due to this non-ideal behavior. So what conditions lead to deviations from ideal gas behavior? Anytime that there's intermolecular forces being increased, so that would be low temperature, high pressure. If intermolecular forces did not exist, water vapor could never condense into a liquid, explain. So in order for water vapor to condense into a liquid, it's got to be attracted to itself. We have to have those intermolecular forces present.